So there's been a new exoplanet discovered, which is a super Earth, and it's thought to be an ocean world. So in this video, we're going to have a look at the planet itself, the star that it orbits, how it was detected, and why we think it's an ocean world. So the planet is called TOI 1452b. Now the B part means that it's the first exoplanet discovered around the star called TOI 1452. And it's about 100 light years away, so it's not particularly close and it's not particularly far away. It's kind of in between. It's not thousands of light years away, and it's not like 4 light years away, which is our closest star. So its radius is about 1.67 that of Earth, and its mass is about 4.8, which is why it's called a super Earth. So it's a little bit bigger than the Earth. It's not small enough that it's kind of exactly Earth-like, and it's not big enough to be classified as a gas giant, which is why we normally refer to these as super Earths. Sometimes we might refer to them as a sub-Neptunian planet, so it's slightly smaller than Neptune, but this one is closer to being the size of Earth, really. Now, the TOI part in the name comes from a TESS object of interest, which means it's been detected with the TESS telescope, which is designed to look for transiting exoplanets. So that's where the name actually comes from, and then the number is kind of the number that it's been detected with. So the star that it orbits is quite a small star. It's a red dwarf. We normally refer to these as red dwarfs because they're quite small, they're quite red in comparison to the sun. And it's about a quarter the radius of the sun and about a quarter of the mass of the sun as well. So a very, very small star. It's a very cool star as well. So because it's redder, its temperature is almost half that of the sun. So it's a cool star, a very small star, which means that its luminosity is quite low. It's not giving out a lot of energy for a star. So that has consequences really for any planets orbiting it, and specifically the habitable zone. So the planet actually does orbit in the habitable zone. So the red dwarf star has a habitable zone. It's much, much closer than our habitable zone. Because it's a smaller star, it's not as luminous. The habitable zone has to be much closer in order for you to have liquid water on the surface of any planet. Now, this planet does orbit in that habitable zone. So it is a temperate planet. This is expected to have liquid water on its surface, which is good. Now, it has a very, very short orbital period of about 11 days. Because that habitable zone is very close to the star, in order for it to get the right temperature, because it's not giving it a lot of energy, it has to have a very, very short orbital period. And to put that into context of our own system, it's about 1/6 the orbital radius of Mercury. So it's very close to its star in comparison to how our planets are set out in our system. But then our sun is much bigger and much brighter, so we don't want planets that close anyway. So even though it's really close, it is in the habitable zone for that particular star. Now, how was it actually detected? So on the left-hand side there, you've got the transit, which is where a planet passes in front of the star. It blocks out some of the light, and it's purely a ratio of the radius of the planet and the radius of the star to how much light is going to get blocked out. So if it's a small star and an enormous planet, it will block out quite a lot, like a large percentage of the actual light from the star. If it's a large star and small planet, it will be the opposite, only block out a very small amount. So we can measure the depth of that dip, and that will give us the radius. We can also get things like the orbit, the semi-major axis, and the orbital period if we measure the time between each transit, each time it passes in front of the star, and it goes all the way around. And then on the right-hand side, you've got the radial velocity of the star. So as the orbit or the planet orbits the star, they orbit a common centre of mass, so it causes a wobble of the star. And we can measure that radial velocity away from us and towards us. Now, the bigger the planet, the more massive it is, it will cause a larger radial velocity on the star, and a smaller one will cause a smaller radial velocity. So we can actually get a minimum mass for that planet by looking at the radial velocity method. So with those two detection methods, we've got the radius, we've got the mass, we've got the orbital radius, and we've got the orbital period. So we've got a huge amount of information about this planet just from those detection methods. Now, why do we think it's an ocean world? Because we haven't imaged it and we haven't seen the oceans on the surface. Well, it comes from the density profile. So it's expected to be a rocky planet. but the density profile we've calculated from the mass and the radius, which we've got from those previous detection methods, suggests that actually it's going to have a significant amount of liquid water on it, which will basically relate to having a large liquid water ocean. So it's that density profile and the composition of the star which is hinted towards as being an ocean world. So we haven't directly observed it as being an ocean world, but it's from the measurements that have been taken that are different from normal rocky planets and different from more of a puffy planet that has an extended atmosphere. It's down to that density profile which we can calculate from the mass and the radius. This is going to be quite interesting when looking for habitable planets out in space. Are ocean worlds going to be better than one that's more Earth-like? Do we want land, or do you think life is actually going to evolve more in the oceans or in water? So thank you for watching, and if you enjoy, then check out some of the other videos.